Welcome to the course on FPGA based signal processing systems. This week we will be looking at the Fourier transform implementations in the FPGA. The part of Fourier transform implementations we will do the discrete Fourier transform and its variants also. Before continuing with the DFT, that we need to know a bit of signals background. So a signal is a set of data or information which is collected from the single source or a multiple source. So this could be having a signal could have the function of independent, it's a function of independent variables. Depends whether it can be one independent variable or two independent variables. The signals are defined accordingly. So the signal can be generated, as I said, that it can be from single source, then it is called a scalar, or multi sources it can be a vector. So if the signal has one independent variable, and that signal is called one dimensional signal. If we have two independent variables, then it is two dimensional signal, and if we have more than two or three dimensional also, if it has n dimensional, in the case more or n or more independent variables will have for the ND signal. So in case of suppose it as a signal which is having the time t, and if we are plotting x of t, so this is a 1D. This xt is varying with here as t progresses. So if we have the image, the 1D signal, if we have an image, for example, then this is x and y, the x varying each pixel in the image. So we take this each pixel amplitude is defined with respect to x and y. So this is two independent variables, and the amplitude of that or the pixel value is depending on x and y location. So that is this is 2D. The image is a 2D signal. The same thing in the video. If we have this x and y variation of the amplitude with respect to one frame and the another frame, this frame is changing. This image is changing in the video for time to time, so that the time is a third independent variable added to it, so the video has become a 3D signal. So likewise, this depends on the independent variables. We'll have this signals classified. The other than that, we can have a signal which is to be called as continuous in time and continuous in amplitude. The one which I had drawn first with the 1D signal was a continuous in time and continuous in amplitude. It is defined at all values of t, and that is CT. CA, the continuous in time signal, also only defined with discrete in amplitude. So in that case, the time is continuous, but the values may be discrete, 1, 2, 3 integer values. Are discrete in time, that is the signal is in time, it is discrete. I mean, it is defined in certain values only, but in amplitude it is continuous. So there is no missing of the values here. In discrete in time and discrete in amplitude, in that case both time and amplitude, these signals are specified in certain instances, not in all the values of t or all the values of a amplitude. So we can see this classification of 4 using a signal x of t, which is having the t and continuous. So this is the signal which is continuous in time and continuous in amplitude obtained from this x of t. The time varies, and then x of t also varies accordingly. So the x of t is defined all values of t. So you have both continuous. So this is continuous in time and continuous in amplitude. So when we sample this signal, that is for discretization, so the sampling yields the result of this signal to be discrete in 1, 2, 3 instances only, where 0, 0, 1, 2, 3, this becomes n now. It's a periodic sampling anyway, or uniform sampling. We can say this is uniform sampling. That means the chopping period is equal in this case, the uniform sampling, or the other case can be a random sampling as well, so in which the sampling period will not be uniform. So here is a uniform sampling in which this signal is sampled, and we get the same value what we have here at this point. It is regular intervals, like a switch. Using a switch, it is captured. The values of a certain instance are captured. Tn equal to 0, 1, 2, 3 and so on. So in this case, the signal is discrete in time and continuous in amplitude. So here still the values are 2.3 and 2, and even then here you can have this 1 and 0, and this is 0.5. These values are not only integer values. So discrete in time and continuous in amplitude is the outcome of the sampling process. this is also, when we do the sampling, we need to know the sampling theorem, which says that whatever the input signal, the signal to be sampled should have the maximum frequency of that signal should be considered for deciding the sampling frequency. That is, that sampling frequency should be at least twice the maximum frequency present in it. So in that case, we will be either band limiting the signal. Suppose the signal is not band limited, we have to band limit it and then apply the sampling theorem. Otherwise, there will be aliasing cases would arise. So the discrete time and continuous amplitude, and this discrete time and continuous amplitude, next if we come to this here. So the same, this signal is quantized. So here the amplitude, you can see it is round off to 2 and then round off to 1, here 0 and here -1. This one is increased the values of 1 here. This is rounding off to 1, and other samples are made zeros. You can see 1 and -2, 1, and also here these samples, all of them around 1 are made as this. The process of quantization are rounding off to the nearest integer. So this gives this is also defined only in the certain instance of the time, that integers, that is discrete in time and discrete in amplitude here. So these are the three cases of signals which we had seen. This would also be part of the ADC and DSC process, whereas this one we can say this continuous in time, discrete in amplitude. So once we have this signal, and if we process it in the DSP or FPGA, after that the outcome of that samples which is coming out of it is first would be like made it like these samples, and then these samples will be made sample and hold it for a while. Till next sample, the value will be hold during the reconstruction process. So you can see that this is the outcome of the continuous in time and discrete in amplitude. And it is kept hold, or the reconstruction process, we get this type of signal. So this is continuous in time and discrete in amplitude. So 4 categories we can have in the signal itself during the sampling and the process. So if we take this in the DSP system, so real world is analog. So whatever we do in the digital thing, and then we have to come back to analog world. So the analog signal which is passed to the analog to digital converter and get the digital signal. After that, it is the DSP or FPGA process that signal. Either your DSP has the filter or FPGA has the filter, or it can be a simple amplifier magnifying the signal, or especially in the case of that what we have learned also filters, if we remove certain frequencies or spectra from the signal, and then the output of the FPGA or DSP also will be digital signal, and this digital signal is again passed on to digital to analog converter, and then get back the analog signal. So the filter designs and everything will get into DSP or FPGA. Now, what is the ADC component? What are those components in the ADC and what are the components in DSC? So what is this digital signal is? Okay, so the analog signal, continuous in time and continuous in amplitude, is passed through the ADC. So the ADC block has the 3 different blocks. You can say it can be outside the ADC, or all of them are part of this analog to digital conversion. So first is the sampling. The sampler, just as a switch, it close and open at a certain interval specified as sampling time of the signal given. So you get the collected signals at the certain points. So this is discrete in time and continuous in amplitude. So the signal which we had looked into here, the second one is the process of sampling. So it is also called the impulse modulator. So the sampling process. After this DT, getting discrete in time and continuous in amplitude, and the quantization happens here. The quantizer, which is the outcome of this quantizer, is near of in values to be made it round off here. That is the process of quantization. So after this quantizer output, that is discrete in time, discrete in amplitude also. After that, 2 or 1 or 3 integer values are passed through the encoder. That the encoding process is done, which gives out only ones and zeros. That is the digital. So when we say digital signal, these are ones and zeros. So this digital signal is getting into the FPGA here, okay, so or the DSP, the filters which you design over here as this module of the Verilog code or this, and get back the output, the filtered output, whatever the processing to be done in this analog signal in digital domain, do that and then get back the digital signal which is also a 0 and 1. So after getting the zeros and ones, which is different from this one which has get into the DSP and FPGA, so this digital signal is passed to the DAC, which does the two jobs here. One is the decoding, the decoder, which is decoding that signal. Yes, this is 2. If it is 4-bit 0 1 0 0, then what is the value of 4 or 6, whatever the value is given. So it is decoding 4 2 1 3. Likewise, it is plotting over the here this values. So 2 1 3. Again, you get the samples of this type here. So this is discrete in time and discrete in amplitude. So that is decoded now. After decoding, it is passed on to the reconstruction process, in which there can be a low pass filter or the interpolator, sample and hold circuits are used, and zero order hold, first order hold, all these interpolators comes into picture of the reconstruction process, and then we get the analog signal. So during the intermediate here after this, you would get this continuous in time, discrete in amplitude, and how good these interpolators are, and then it is 2 and 1 in between, how this needs to be connected are decided by the interpolator, the best interpolator, the reconstructor used in the process of the D2A. So then we get the analog signal. So it's coming back to the real analog world. So the signal process, the signal processing system will have all these things. The digital signal processing system will have all those things. So they are learning about the coding of this FPGAs, and before that, those signal needs to come through the ADC and then get back to DAC here. So with this background, we will move on to the some of the mappings. Before learning the Fourier transforms, we need to know what is the time and frequency domain mapping. So in the time domain and frequency domain, if the signal is continuous, if it apply a Fourier representation or Fourier transform or Fourier series, okay, here depends on it is periodic or periodic. So the spectrum, the outcome in the frequency domain will be aperiodic. If the signal is only continuous, that is mapping into aperiodic. It is discrete, the frequency domain gets into the periodic after the transform. Periodic, if here in time domain it is periodic, then it is mapped into discrete here, and aperiodic again goes to the continuous. So this is just a mapping for this, and suppose signal which has continuous and periodic. The signal is continuous, it is defined all at all time instance, and it is also the pattern repeating, and we have the special case for this periodicity as well. So if it is continuous and periodic, then we will be using the continuous time Fourier series, okay, and that would give us the spectra which is aperiodic. Continuous is mapping into aperiodic, and periodicity mapping into discrete. So you will have the spectra which is discrete in nature, and also it would be aperiodic. It won't be it won't be repeating, the pattern of the spectra won't be repeating. So if it is continuous and aperiodic here, so then the Fourier representation or Fourier analysis should be done with the continuous time Fourier transform, that's aperiodicity. So this maps into the continuous mapping into aperiodic mapping into continuous here. So you will also have the spectrum will be aperiodic and continuous. So it won't be repeating and continuous. So if you here again, if you have this discrete one and periodic, the signal is discrete and periodic, then the discrete time Fourier series, so to get the spectra of this signal. So how this mapping is periodic, and the periodic maps into discrete. So this spectrum would be periodic, repeating in nature, and discrete. Discrete and aperiodic will be having this discrete time Fourier transform. This is used to this. So periodic, discrete maps into periodic, and the aperiodicity maps into continuous. So this signal is periodic, whether it is continuous or discrete will be a Fourier series representation, or the analysis to be done with Fourier series, and then if it is aperiodic, then Fourier transform. Whether it is continuous or discrete depends on that continuous time or discrete time, and we used to get the spectra. So we should be knowing the mapping, so that whether the outcome of the Fourier transform applied to the signal is correct or not, to verify that. So now coming to the discrete Fourier transform, we will take up a signal. From that signal, we will try to understand what is that DFT is doing. So taking a continuous time signal x of t, which contains 1 kilohertz and 2 kilohertz frequencies, and this is sampled at frequency of 8 kilohertz. So if we take that signal, suppose x of t equal to sine of 2 pi 1000 t, that is 1 kilohertz, and its amplitude is 1, and the next part of that signal is 0.5, the amplitude is 0.5 sine 2 pi and 2 kilohertz, which is 2000. It has a phase shift as well, 3 pi by 4. So now to take this, this signal, this will be discretized, and then this is continuous time signal. We have to we are going to sample it to apply the DFT here. So DFT will be the sampled version of that DTFT which we had there in the previous slide. So x of t, to find the DFT of this, find the 8-point DFT of the signal. Actually, we perform the DFT to get the frequency components which are present in the input signal. So to analyze it, what are the frequency component present? The spectra reveals that information of what is the frequency present in this particular signal, what is the amplitude of that signal, and that amplitude of this as well as the phase of that signal with respect to the fundamental cosine of the signal which is present there. So it gives the magnitude, phase information, and the frequency content present in the signal. So the 8-point DFT of that signal, to take 8-point DFT just for the explanation which we are going to make later. So we have this x of t is now made as in sine components, or made as cos. So that cos sin theta equal to cos theta minus 90. So that's what we did, 2 pi 1000 t cos t minus t pi by 2, 90. Similarly, this component 0.5 cos 2 pi 2000 t plus 3 by 4, that is a phase shift minus pi by 2, which is just for an understanding. It need not be done in the process. We will correlate the results with respect to this particular form of the expression, that expression. So now this signal is plotted, that x of t is plotted over here, which has two components, sine 2 pi 1000 t and 0.5 2000 with the phase shift. So this is the second component, the pink one, and this one is the first component. So adding 2 will result in x in of t, or x of t, which is going to be, now we are sampling this one. So you can see the line blue, which is the signal which we are going to take the DFT for that. So the sampled sequence, how to obtain? So DFT would take the discrete samples only. So we need to discretize this here. So x of n now equal to 2 pi n by t. So n is substitute t is here as nts. Okay, so the ts is fs is given as 8 kilohertz. So 1 by 8 comes here, 2 pi 1000 nts by 8000. So that is why 2 pi by n has come here, 0.5 sine 2 pi by 4 into n. Similarly, 2000 by 8000 here. So this 3 pi by 4, the signal is now, this is the sampled signal what we have. And this 8 kilohertz is good enough to, because the maximum frequency here is 2 kilohertz. At least it should be sampled by 4 kilohertz, right, according to sampling theorem. So we are making it 8 kilohertz. That's actually good to just to illustrate here. It is fs equal to 8 kilohertz. If we sample it, we get the samples from that signal as this. These are just numbers 0, 1, 2, 3, 4, 5, 6, 7. So 8 samples will be there. So this is sampled, and then what is the DFT equation here? DFT equation is x of k, n varying from 0 to n minus 1, x of n e power minus j 2 pi k n by n. For k is the bin index, which refers to k is varying from 0 to n minus 1, as n varying from 0 to n minus similarly. So k represents the bin index, which is, if k equal to 0, this expression gives the DC component present in it. K equal to 1, we will get the fundamental, k2 second harmonic, and so on. But it is not like the n minus 1, all components are independent. So we will see the dependency between the components what we obtained from here, though it should be done for DFT 0 to n minus 1. So we get 0, k varying from 0 to 7 in this case, n equal to 0 to n minus 1. What is this one doing? is here x of n equal to e power minus j 2 pi k n by n. So, this is the signal, the sample version is shown here. The samples what we got is from 0, 1, 2, 3, 4, 5, 6, 7, 8 samples over there. This is n, this is x of n. So, now the endpoint DFT equation is known. So, would like to hear the x of n, which can be written like x of n into cos 2 pi k n by n minus j sin 2 pi k n by n, right. This e power j can be written over like this, summation n equal to 0 to n minus 1, that is x of k. So, what are we doing actually in this process is that we are correlating this x of n input signal with cosine signal, and then correlating with this sine signal, and check whether there is a correlation between this signal or not. So, what is the correlation which when we put k equal to 1, that is representing the fundamental which is present in the signal. So, the fundamental cosine signal for the value n equal to 8, whatever is we are doing endpoint DFT 8 or 9, DFT can take even the odd numbers. So, n 2 pi k n by n cosine signal and correlate it with this. If there is similarity between these two, there will be a higher correlation coefficient. Similarly, sine and cos, the sine and x of n, we correlate it. If the both are having the similarity, then this summation would result in a value. If there is no correlation, or if it is this type of cosine signal, a sine signal is not present, the correlation would result in a 0. So, that means that this type of signal does not exist in the x of n. So, that is actually the meaning of the DFT what we are performing. So, when k equal to 0, that means we are trying to check whether there is a DC component present in it or not. So, k substituting 0, bin index 0 in this, k is 0, this becomes n is varying from 0 to 7, this result in 0, 1, 2, 3, 4, 5, 6, this is sample itself. Sum it up, the samples what we had. So, those samples are giving here, those samples adding up together is giving 0. That means your x of k, when DC component is absent completely, there is no DC component present in it. It is true also in our signal what we had taken, there is no DC present in that. And then x of 1, we do with this substituting this k equal to 1, the bin index 1, and vary n equal to 0 to 7. So, x of n. So, what does it actually represent here? So, if you see x of 0 and n varying from 0 to n minus 1, and k is 1. So, this e power, this results in minus j 2 pi by 8, and the computation goes on with the things what. So, we will get x of 1 as some complex number 0 minus j 4 for this. So, it is 4 angle minus 90. So, similarly for k equal to 2, so yeah, there is some presence of, it shows that fundamental is present, which has a magnitude 4 and minus 90 degree, and it is the fundamental is present. We had that there is a sine 1000 hertz, that is 1 kilohertz was there in the signal what we had taken, that is the fundamental. And then, so it has the magnitude showing it is 4 and minus 90. Let us interpret that, how does it become 4 and minus 90? The magnitude what we have taken is 1, right, in the sine 2 pi 1000 t, and there is a phase also. So, but in sine case, sine of, there is no phase. So, what is the DFT is giving here? Okay. So, in x2, when k equal to 2, that is second harmonic, bin index 2 refers to the second harmonic of the input signal, n is varying from 0 to 7, xn e power minus j 2 pi 2n by n, k is 2. So, if we expand this, vary the n values and then substitute the values, and then we get that value, what we get is 2 angle 45. Yes, it shows the presence of second harmonic. So, yes, it is true also, we have the 2000 hertz signal in that. So, when we make that k equal to 1, that is, we have represented this as m. So, it is showing that k equal to 1, in which this is the input signal, and if you see the one which is, this is sine and this is cos 2 pi, k is 1, 2 pi by n, sine 2 pi k n by n. Okay, so k equal to 1. So, the sine and cos what is for k equal to 1 is shown here. So, we can see this, the fundamental width. Okay. So, it goes up to the signal points what we had taken. So within that period we are assuming that this one, so this is also going to here, the 7 is plotted, still a few more here, 7. If you show that, if you see that this is completing one cycle over here up to this point, and similarly this is completing one cycle over here. So within the n samples, that is one cycle of the waveform related to the n and 2 pi is this thing. So the DFT is performing correlation between this sign and this, and taking the coefficient and performing the again correlation between this cos and the input signal. Okay. So what is the similarity between these two? So what is the similarity between these two? Actually, that's what the DFT equation gives. If there is a similarity, yes, it results in a value. Otherwise, that gives a 0. So there is no similarity between these two signals in that XFN and this. So this is with k equal to 1. When k equal to 2, what is that? It is this is the input signal, which is xn or x of t, and the sample version we have here. So the k equal to 2, which is having the sine, and this is cos. So sine of 2 pi k n by n, where k is 2 and this is cos 2 pi k n by n. So this cos and sine signals we have. So again it is finding the similarity between this and this, and similarity between this and this, the input and the cosine, input and sine. So the similarity between this, which if it is there similar, then it results in the DFT equation. The output is yes, there is a number, otherwise there is no. So in case of DC, there is no correlation we have seen. And if you look at the k equal to 3, similarly within the n samples, it takes 3 cycles of 1. You can see this is 2 and the third one is completing here. So here is that this is again taking the complete cosine signal, okay, of these points, and correlation between these two and the correlation between these two are computed, k equal to 3 here. So within n points, when k equal to 1, it completes one full cycle, and if k equal to 2, that completes 2 cycles, and k equal to 3 would complete 3 cycles. So likewise, the sine and cos as correlated with the input signal and get the correlation coefficient, correlated value. So x2 is, it shows some of the values here. And then x3 similarly, if we do that, if k equal to 3 and it results 0, yes, there is no third harmonic in this. Fourth is k varying from 0 to n minus 1, so we vary up to 7 here. K is x of n e power minus j 2 pi k n, so this is also 0, and then 5, this is also 0, this is not giving any outputs here, and 6, yes, having some value, but there is no sixth harmonic in this. Why 6 is giving a certain value, and 7 similarly having some values for angle 90. So we have computed k up from 0, 1 to n minus 1, which is 7. Okay. So what are the components which we actually had from this magnitude spectra? You can see 0, 1, 2, 3, yes, fundamental is shown and second harmonic is shown. Okay. Third harmonic is not present, 4 is not there, 5 is not there, and 6 is present, and 7 is present. So here we have the n by 2, 0 to n by 2 independent terms in that 0, that is 8 by 2, 4. So up to this 0, 1, 2, 3, we have this independent terms, and then with respect to 4, it is a conjugate actually. So you get in the magnitude you get the same, but in the phase you would be looking at the antisymmetric thing. So this is 3 is same as 5, and 2 is same as 6, and 1 is same as 7, and 0 will be repeating again 8, because the spectra is going to repeat. So in DFT what we get is the n by 2, or 0 to n by 2 minus 1 here, that is components are independent and the remaining term are redundant. These components are redundant, So we need not compute when you have this 8-point DFT. If you compute up to 4, that is giving the independent terms. And the magnitude and phase, we have the similarly, you can see that minus pi by 2, pi by 4 and so on. So this is antisymmetric, and here magnitude values are here we have this, these are conjugates. So now what is the meaning of this 4 here? But we had the sign fundamental magnitude is 1, right? So it is giving 4. So this magnitude 4, what we have got into this 2 by n, the scaling, we get 4 into 2 by here 8, okay. So this would result in 1. So this is the actual magnitude of the signal which was present in the input signal, the magnitude is 1. So similarly here for second harmonic, we have getting 2, that is 2 by 8, which is 0.5. So 0.5 is the amplitude of the signal of the second harmonic to 2000. And the k representing the frequency spacing will be giving that what is the frequency space, that is equal to fs by n. What is the sampling frequency by number 8-point DFT, a number of samples taken over here. So 1 and 0.5, this is related to the amplitude. What about the phase? Okay, for the first one, that is fundamental component, doesn't have any phase, that is sine 2 pi 1000 t. And when we convert into cos, we observe that there is theta minus pi by 2, that is pi by 2. Right, in the second expression I said it was for understanding. So the fundamental shows that there is a pi by 2 shift. So with respect to the fundamental, yes, it is having the fundamental is minus pi by 2, and the second harmonics having pi by 4, that is 3 pi by 4 minus that is pi by 2, we have this 3 that is pi by 4 with respect to the fundamental, it gives 45 degrees. So that representation is the phase information we get from this. So 3 and 4 does not exist, only 2 components were there, and these 2 are again the conjugates, and these are redundant as well. So this information, so this is the information we get from magnitude and phase spectra of the DFT. So what about the DC signal? The DC is not present, it shows 0. When DC is suppose present, this scaling factor will be 1 by n, that is whatever the DC into 1 by n will be the actual DC present in the input signal. So likewise all this 2 by n scaling will be valid for all harmonics except that DC. So now getting into the real spectra, suppose complex number is now separated into real and imaginary parts and plotted over here. For that it is giving that this is real spectra, and the imaginary one shows that the spectrum. This is just a representation of the real and imaginary one. And the properties, if we look into the symmetry for a real sequence of like x, the one which we had taken, xk equal to x conjugate n minus k, 8 minus 1. So or 7 8 minus 1, it will be 7. So 7 and this 1 will be equal. So that is the complex conjugate of each other. So that can be identified from here. Similarly, if k equal to 2 and 8 minus 2, this is 6. The conjugate of this is x2 is conjugate of 6. So there are n by 2 terms are independent of xk terms, and that is 0 to n by 2, and n by 2 plus 1 that is this term which we had seen, and n minus 1 are redundant information, just a conjugate of these terms. So it does not provide any additional information about the spectrum. So for the analysis frequency, if you want to take what is the analysis frequency, that is k into fs by n. So if you want, suppose we take a 50 hertz, and this is k, and fs is the sampling time, and n is suppose 128. So we should keep for fundamental k equal to 6400 hertz, f into 128. If you increase this k to 2, then it should be 100 hertz, and fs should be 100 into 128. So this relation needs to be maintained when we sample it. Okay, so we can get the analysis frequencies. K is the bin index or the harmonic number here. So DFT is linear, and if we have the one signal x1n and x2n, so you can take the DFT of it x1n separately and x2n separately and add them. That would be xk, which is the addition of 2 signals, and take the DFT, that would be the same. it's linear. So, DFT magnitudes for real input signal, as I told that for DFT kth output magnitude, for the fundamental, for our case it was showing 4 into 2 by n, that gives the amplitude of the signal, which is valid for all harmonics except DC component. 4 into 2 by n, we got 1, and the next one was 2, the second harmonic gave the amplitude 2, and 2 into 2 by n, that is giving 1, n is 8 in that case. So, the phase information which was with respect to the fundamental pi by 2, we observed that in the phase information. DC component, this factor is 1 by n, so actual value of the DC component. So, the DFT frequency axis, k equal to 1, 2, 3 represents Fs by n, the sampling frequency by n, here 8 kilohertz and n is 8. Okay, so that is each one is 1000, 2000, 3000, 4000 represents. So, k 0, 1 represents 1000, 2 represents 2000, 3000 and so on. So, that is this frequency spacing which is decided from the sampling frequency and the n samples considered for the DFT. And the DFT shifting theorem only would like to give X shifted DFT can be obtained from the DFT of the signal which is not shifted, which we had now. Suppose we found that x of k. So, if you want the signal shifted signal in time in either in the left side or right side, then it can be multiplied accordingly with the factor e power j 2 pi k n by n. This n is a shift we can apply, and that shift, if we know the spectrum of the signal, and the shifted spectrum also can be obtained from this. That is a property of that. So, n is positive if that is a if shifted left, n will be negative if it is shifted right. The magnitude will not be affected by shifting. So, that helps in this property helps in the DFT of sliding the number of samples and taking the DFT for different samples. So, the phase shift gets affected. Suppose you take the signal this x of n and shift it x n plus 3. So, that is having this 1.06 over to here. Okay. So, this is a shift we have made, and this signal x k is known, right. Now, we have found from k is varying from 0 to 7. Okay. So, what is the spectrums for this case? For example, if we take k equal to 1, what we got is this is 4 angle minus 90 or 4 e power minus j pi by 2. So, what is the shifted spectrum k equal to 1 will be? So, shifted 1 will be, so e power j 2 pi k n by n, j 2 pi k is 1 and n is the number of samples shifted. Here it is given 3 now samples shifted in the time. So, it is positive left shift, 4 e power j is the x of 1, which is the unshifted one, the one x of n. So, if we have this, you can get 4 e power j pi by 4, the 4 angle 45 is the shifted spectrum k for k equal to 1, and similarly k equal to 2, 3, 4 also can be found in this. So, if you know the signal of the DFT of this and the shifted DFT, shifted signal DFT for number of sample whatever it is, if it is one sample, then it is going to be 2 pi n by n, k is actually the bin index here it is 1. So, we are talking about the fundamental. So, if you are interested in only one component, just fix k equal to 1 and will be, and the number this shifting either left or right can be made here. So, shifted in signal DFT can be found from this. So, with this I would like to give the DFT information, that is that we have seen the signals and classification of the signals, and either the DSP system generally has the ADC and DAC. What are the parts of ADC and DAC? What are the significance of those signals which we had, the classified signals? By knowing them, what is the sampling process? If you want to do the DFT, and you should know the signal characteristics, like it's a continuous time or discrete time, periodic or aperiodic, so that appropriate Fourier analysis or transform can be applied. So, if you want to apply DFT, and we are just doing the correlation between the input signal and the fundamental input signal and the second harmonic, third harmonic, and if they are similar, that would result in a coefficient which is nothing but the magnitude and phase of that information obtained from the DFT. So, we have seen the plots of the magnitude and phase spectra and the symmetricity of that, and how do we relate this DFT output magnitude to the actual signal, which is the signal amplitude under the phase. So, DFT gives the frequency component present in the signal and the harmonics also, and whose magnitude and phase. So, this interpretation can be understood from the DSP explanation. We'll look at the Fourier transform and DFT's variance and the fast Fourier, and how we can use these signal processing algorithms in the FPGA, making the Verilog code, IPs, also the DSP builder or the system generator of the third party tool of this MATLAB Simulink, or those can be used for developing these Verilog modules or targeting the FPGAs through them for these signal processing algorithms in the coming lecture. Thank you.